Hello everyone, welcome back. Let's continue. So, today we will talk about design for stiffness, and today we will concentrate on optimization with respect to material usage. So, as we discussed earlier, if there is a axial force on a member, so either in tension or compression, what happens that the entire cross section, so whatever area we have here, so the load will be distributed all over the area and the stresses will be uniform. So, there will be uniform stress distribution whenever there is a tension and compression. So, in terms of material usage, definitely this is what is desired. So, we want to have longitudinal forces coming on the members, and that is why when we are looking for high stiffness, we want that on the links or the elements, the forces should be in the longitudinal direction. On the other hand, if there is a bending load, so if there is a force acting at the end in this case, so there will be bending load, and because of that what we observe that the stresses are not uniform. So, there is a large difference in local stress value, and what we notice that, so even at a different place the stresses are different, and along the cross section also. So, for instance, here if we see, so at the top layer we have the maximum tension, and at the bottom layer we have the compressive load, and in between it will vary. So, we will see a large variation. So, 0 along the neutral axis, and then again negative direction, the is a compressive load at the bottom layer. So, it is a maximum at the top and bottom layer, but in between the stresses are really small. And what we understand with respect to material usage, the material in between. So, if we just leave the top and bottom layer, what we understand that the middle layer will not take much load, and yeah, in terms of material usage it is not very good design. So, that is why we ask, whenever if we we can avoid, we should try to avoid loads coming in bending, or if it is there, then we try to find a way that how we can stiffen it, how we can maximize the material usage. So, just for comparison, so if we have this truss and we take a thin sheet here, so having thickness T and the height same height h in both the places and length also same. So, if you try to compare, and if there is a vertical load acting here in both the cases, so we try to make it similar. And what we also mentioned that the volume of the triangular truss what we have here 1 and 2, so is equals the plate construction. So, overall volume is same. When we are talking about the trusses, we also solve one example, and what we are saying that the area of cross section AL and AB are such that the deflections at F are same. So, evenly distributed. So, we found the relationship, and then we will calculate what is the difference. So, if this is the scenario, what has been observed that if we try to plot k over E t with respect to L over H. So, the truss and the sheet. So, more or less if it's we can say, we can generalize that if it's L over H is greater than 1, they have the similar stiffness. So, both will follow the same path. As the L over H is smaller than 1, so if it is getting shorter, so this one will have higher values. So, what we can see, and the main reason is when it is getting shorter, the bending stiffness and plus the shear stiffness, because it is a short. So, that will come into picture, and therefore, the stiffness will be way higher. So, yes, what we can say that the thin sheet with the similar dimensions, if is the L by H ratio is smaller, it will have a higher stiffness, but if L by H is larger, both will give similar performance. And what we realized that maybe the truss construction might be preferred because is because of the age of manufacturing and how it can be constructed. So, because the stiffness wise is the same, and a very thin sheet will have other kind of problems. So, it is prone to warping if the forces are really high. So, yeah, for that reason also we tend to use truss structure. What we also realize that in case of trusses, the kind of forces coming on the members on the links is again longitudinal. So, either is in tension or compression, and that also qualifies that the weight or the stresses are evenly distributed on the links. So, we just try to generalize it, and can suppose just take this construction where we have this alpha and beta from the vertical and force F is applied. So, we have done a similar example earlier. So, just take this case and quickly we go through. So, if force F is applied, what is the deflection because of the stiffnesses KAC and KBC, and we try to calculate what is the effective stiffness along F. So, what we also understand that in this case the total deflection or the compliance is the sum of the two. So, WAC and WBC. So, where these two deflections are calculated assuming the other member is infinitely stiff or rigid. So, we will try to calculate again and try to solve. So, for instance, in this case again is a binary element. So, forces will be along the links. So, we can construct the force diagram. So, this is F, and then we have this along BC, and this force will be along AC, and when we close we will get the directions as well. And of course, the angles are here. So, alpha and beta. So, if we just use the sine rule, here we can write FAC over sine beta is equal to FBC over sine alpha. So, the opposite angle equal to F times this angle, which is 180 minus alpha minus beta. So, this is the relationship we get between the three forces, and therefore, what we can write is FAC in terms of F. So, we will just transfer, and what we realize the F sin beta over sin alpha plus beta, this is what we get FAC in terms of F, and then force along BC or on link BC is FBC, which is again F sin alpha divided by sin alpha plus beta. So, in the numerator we are getting sin alpha and sin beta, and in denominator is a sin alpha plus beta. So, that is the function we are getting, trigonometric function. For calculation of the deflections, we can proceed similarly. So, what we assume in the beginning, what if is a KBC, the stiffness of the link BC is very high. So, infinitely rigid, and what is the contribution because of the deflection or the stiffness of the link AC. So, what happens if it is here and if force is applied, it will reach here C prime. So, we call it. So, this is the deflection W2, and since it is a rigid, so it will make 90 degree, and then it will come here. So, accordingly, so we will drop a perpendicular here, and then so W2 is the deflection because of the force applied, but what is the deflection along AC, that is the W1 here. So, we drop a perpendicular and we find W1. Similarly, we drop a perpendicular from point C prime and we can get WAC here. So, similarly, we can write W2 in terms of W1. So, that is the relationship. So, this is the angle beta, and since it's this is 90. So, this angle will be 90 minus beta, and when it comes to this angle, this angle is alpha. So, this entire angle is alpha again. So, that will be alpha minus 90 minus beta. So, therefore, W2 will be W1 cos alpha minus beta minus 90 degree, and this one we can write W1 sin. But we also realize that WAC can be also written here in terms of W2. So, W2 and this angle 90 minus beta cos, and then it will be sin. So, we will get sin and W2, and then here we can write in terms of W1. So, W2 is here W1 by sin alpha plus beta and sin beta. But we also know that the W1 will be nothing but the force coming on link AC divided by the stiffness KAC, which will be EA by L, right. So, this is the stiffness, bending stiffness, and therefore, WAC can be written as, if we substitute, what we can see that is a FAC over KAC into sin beta divided by sin alpha plus beta. So, if we want to write WAC with respect to F, then we substitute FAC with respect to F, and then we again get the parameter sin beta divided by sin alpha plus beta, and that is why we get the square term here. So, F over KAC times sin beta divided by sin alpha plus beta square, and if you want to calculate the effective stiffness, so it will be F over WAC, and this is what we will get. So, this is the effective stiffness. This we can also think of in terms of transmission ratio. So, that we can also do that. So, similarly, we can calculate WBC also. So, for WBC, so the deflection because of the KBC. So, now this is finite, but this is assumed infinite rigid, and then similarly we can derive and we can find what will be the deflection in the vertical direction, and similarly we can also calculate the effective stiffness along F. So, when we summarize, these are the two deflections we just found and can be written in terms of F and stiffnesses KAB and KAC and KBC, and in terms of alpha and beta. So, this is the formulation and this is what we get, and therefore, what we can write is, if is the we are looking at the total stiffness, effective stiffness, we can write F over W, the total deflection, and that can be in turn written F over FWSC plus WBC. And if we all put everything together, this is the formulation we get, K total. So, 1 over KAC times sin beta divided by sin alpha plus beta square plus 1 by KBC and sin alpha by sin alpha plus beta square. So, it looks complicated, but for general configuration this is what we get. But we also realize that sin alpha plus beta, if we put alpha plus beta equal to 90 degree, actually then sin alpha plus beta will be sin 90, which is 1. And if we also assume that the stiffness KAC is equal to KBC, for instance, if we assume that it can come out, and what we will be left with is also the beta and alpha are also related. So, since alpha beta is 90 degrees, so one will be sine and one will be cos square. So, sine square plus sine square alpha plus cos square is 1. So, it can be further simplified. So, what we will find, yes, this also, if we put alpha plus beta equal to 45 degree, that also alpha plus beta is 90 degree. So, we get that formulation, and this is also there. So, actually one can say that this may be the sufficient condition of alpha plus beta equal to 90 degree can give us the optimum result, and in that case we can get K total, the effective stiffness is equal to just K, whatever is the stiffness of the individual links. But if we try to recall, what we also understand that in terms of material uses for the given length, what we understand that yes, we can make KAC equal to KBC, but at 45 degree both will be the same, the lengths will be same. So, then the area of cross section will be same. So, we will get the most optimized value, or what we can say that in terms of material uses we will get the stiffest configuration. So, that is why alpha plus alpha equal to beta equal to 45 degree we will get the optimum result. And what we should also understand that in this case the effective stiffness will be K. So, it is a very good result, and then we can cross check also for different kind of configurations. And what we also realize in this case is actually the configuration is nothing but this is 90° and but what we are looking at is maybe just 45° where 45 and 45, which will give us the best result. So, in order to compare, and suppose if there is a bending load, like what kind of sections, what kind of profile we should use, so that we can maximize the stiffness. So, of course, we want that if we want to have a higher stiffness, we should always aim for construction, so that there will be forces in the longitudinal directions only. But many times it is not possible, and there will be other kind of loads also coming. So, bending or the torsional load. So, how to stiffen the structure in that case? So, for instance, if there is a bending load, so how to maximize the stiffness? So, if we just try to compare, and for that if we take thin wall profiles with equal mass per unit length. So, what we are trying to do is we are trying to use the similar kind of construction. So, weight wise is the same, equal mass per unit length. So, length is also fixed, all other parameters are fixed. So, then what we are playing with this 4b. So, 4b is the perimeter and T is the thickness we are talking about. So, this is what we are, this is the in a way is the area 4b times T, and we are playing with that, and if we just compare, then we will find that what kind of section should be best to use for higher bending stiffness. So, if we just take a case of cantilever beam, what we realize that the stiffness, the bending stiffness is 3 EI divided by LQ, and if we just fix all the parameters, then KB is just function of I, where I is, if this is my cross section and this is the axis, suppose this is call it depth, this is the depth and this is B. So, I is nothing but B dq by 12. So, if we just take the square one as a reference, so B width and the height, and T is the thickness, and if we take the compare the ratio I x over I box or I naught, what do we say? So, of course, this is 1, and now we are distributing. So, suppose if we just increase the height, so the width 1 by 2 b, but then the height will be 3 by 2 b, in this case 27 by 16. So, it has increased because yes, we are increasing the height where the stresses will be maximum, the top and bottom layer, and we can redistribute, and also we can push it further. So, width we can take B, and then this height will be 2b. So, it is a I section, in this case it is 4 times more higher than the square section. If we push it further and limit it to 0.5 b, and then this height is 3 b, it has increased to 6.75. And suppose if we just make it a straight thin sheet, if we take just thickness T and height total height 4b, then what we realize that compared to the square cross section, it's 8 times higher. So, if there is a bending load and if we really want to have a very high stiffness, the ideal profile should be the section should be just a thin sheet flexures or thin sheet we will call it later. Yes, we call when we talk about flexures we will use that term, but for the time being what we can say just it can be simply a thin section. Of course, what we also need to remember that if it's a thin section, then yes, it's a if there is a large force bending load coming, then it will be prone to warping, and any asymmetric load, off axis load will cause a lot of problems. So, therefore, if we have to use this, we have to use with the caution, and we should be aware of what are the difficulties if we are going for that kind of design. But yes, ideally a thin sheet, if it is supported from the sides and if there is a vertical load, the highest bending stiffness we can get in that case only. And this can be applied also. So, for instance, if this is the design and if so suppose load is there, so large bending load is there. So, of course, it is asymmetric and there is a thickness, but if we really want to use that, what we can always do that we can go for a sandwich structure. So, symmetric design, and we can increase the stiffness. So, coming to torsion, what happens if it's a thin walled tube? So, if there is a torsional load, so as I mentioned, many times it's very difficult to avoid certain kind of loading. Ideally, we want that there should be longitudinal force only, but the way the machines are designed, the bending and torsional loads can also come. And if we are really looking for higher stiffness, what are the parameters, what are the designs we should look for. So, for instance, if you are talking about thin wall tube, so very thin T, so thickness T, uniform thickness, but it's a close profile, and what we realize that in this case the rotational stiffness is Gk over L. G is the shear modulus and K is this parameter. And when we look at this parameter, what we realize that the entire area enclosed will come into picture, and all the shear load will be uniformly distributed, and it will be taken over by the entire area. Although there is no material inside, so only the outer section with the very small thickness T is there, but when it comes to the taking the load, what we realize that the A enclosed, so area enclosed will come into picture, and that is the region that if it is a closed tube, it will have a very high rotational stiffness. So, we can also compare. So, suppose we just divide it and put it in this fashion. So, top and bottom layer with the pi d by 2 and apply a moment here and try to compare the two, a tube and with the two flat sheets, apply a moment. We get a similar kind of a stiffness, torsional stiffness, except yes, in one case you have E G shear modulus and the other E. So, Poisson ratio will come into picture, and then okay. But apart from that is similar, and from the bending one we already know that if you apply a moment like this, the top layer will be in tension and the bottom layer in compression, and that will give us the best usage of material. And similarly, for torsion, the thin tube will give us the best result, because the entire the area, the cross section will take the load and provide us the sufficient rigidity or the stiffness. So, in order to compare again, we can again do the similar thing, and we can again compare with respect to the square cross section and 4B and thickness T, and we try to redistribute. So, in this case is 1. If it's a triangular structure, it's reduced 0.59. If it's rectangular, 0.5 B and 1.5 B, it has further reduced. If it's a longish and suppose is 0.1 B and 1.9 B, it has reduced to 0.04. But if we take a tube, circular tube, that gives us the best results, which is 1.6 times. So, of course, for the taking the torsional load and talking about the stiffness, the best is to use thin tube, circular tubes. Yes, here I think important to note down that this I is not J all the time, the polar moment of inertia is only valid for circular cross section. If it's not circular, then it will be different, and yeah, means there are some general formulations, and we can always refer to text for that. So, again, for high rigidity in torsion, high stiffness in torsion, it's a better to use thin tubes, circular tubes, and that will give us the best result in terms of stiffness. So, if you want to compare, we can quickly go through that. So, we just talk about solid circular shaft, and if we are applying a torsional load T, length L and diameter D. So, the shear stress will be given by Td over 2 IP, and the rotational stiffness is G IP by L, where this IP is nothing but the polar moment of inertia, because it is a circular section. So, pi d to the power 4 by 32. So, this holds true for the circular cross section. If it's not circular, yes, we have to refer to the text, and we can use it accordingly. What happens if it's a thin tube? So, suppose if you want to compare the stiffness of the two, so one is the solid and the other is thin wall cylinder under torsion. So, what we find that we can write the rotational stiffness. So, for solid shafts it's a GIP divided by L, and we can always replace IP with the pi d power 4 by 32. So, this is what we get. For cylinder, yes, the IP value will be pi dq T by 4. So, if you are interested, you can always use the formulation. So, IP is pi 32, and here d to the power 4 minus d to the power 4, and we also know that d minus d will be 2t, and assuming that t is very small compared to d. So, if you take that assumption, we should be able to derive it. So, we can get this formula for K cylinder, the stiffness, rotational stiffness of the cylinder. So, if we compare and write, so if it's the same material, so everything will get cancelled except the geometric parameters. So, capital D and T and the small d, the small diameter. So, we will try to see the implication. So, we will take one example. So, for instance, if we just take a cylinder, thin wall cylinder with the capital D 100 millimeter and the small t the thickness 1 millimeter, and on the other hand, if we take a solid shaft with the diameter 20 millimeter only, what happens? So, if we compare, what we realize that the thin tube is 50 times stiffer than the solid shaft. So, it's always better to push the material or put the material away from the center line. So, if it's farther, and that we can also understand that when we when we apply any torsional load, if we give any torsional load, the farther from the center, the forces will be smaller, and therefore, it can take the deformation will be small, and therefore, the stiffness will be higher. So, that way also we can see, otherwise we can definitely use this formulation and can compare ourselves. So, if we want to compare the circular section, so using different criteria, so we can think of a thin tube. So, here is D 100 millimeter and thickness is 0.25 millimeter, other is so D 50 and D 49 and T is 0.5 millimeter. So, if you are talking about the weight, so equal weight, the diameter for the solid shaft is only 10 millimeter. So, this is the general formulation we can get. So, of course, for equal weight, if everything is same, then what we have to compare is the area of cross section. So, area will be same, and that can give us this formulation. If we are looking about the strength, then we are talking about the stresses. So, tau r T by J Rho P. So, yes, I think then if we talk about this, T r by J, and J we can write in terms of D, and then we should be able to arrive at this. So, what we is the same again, but now you can see that the solid shaft diameter of solid shaft has increased to 27 mm. So, for same strength. If you are looking for equal torsional stiffness, again we can compare, and the torsional stiffness we can compare, we just derived and compare, but we find d small d over capital D to the power 4 is equal to 80 by d. And what we realize that the diameter of for the same thin tube, to get the same stiffness, the diameter of the solid shaft has increased. If we just put together and try to compare, what we realize that in order to get the same stiffness, the solid shaft is quite big, or what we can also say that if we want to have equal torsional stiffness, it's always better to spread it and take the thin tube, and that will give us the best result. So, we can always take these cases one by one and can say compare the other parameters. So, suppose if you are looking for the same equal weight, what will be the ratios of K, K1 and K2, what will be the difference? Similarly, if this is the case, if you are going for equal strength, what will be the stiffness ratio? And similarly, we can check for torsional stiffness, we can do other way around as well. So, for the same torsional stiffness, if you are going for solid and thin tube, what will be the difference in weights? So, vice versa. So, we will stop here and we will continue from here. Thank you.